This presentation aims to gain insights into the diffusion of a variety of gas molecules inside metal organic frameworks. All the examples of gas diffusion in metal organic frameworks considered in this presentation deal with microporous metal organic frameworks with effective pore dimensions less than 2 nanometers or 20 angstroms. If we have a look at the Lennard-Jones potential energy of interaction between three gas molecules, hydrogen, argon, and methane, with a pore wall, we see the repulsion forces dominate close to the wall, followed by attraction forces that reach a minimum value and then reduce to zero at a distance of 1 nanometer from the wall. The potential energy well for methane is much deeper than that for argon and hydrogen, signifying that methane has a stronger adsorption with the pore wall than argon, and argon is stronger in its interactions with the wall than hydrogen. Beyond a distance of 1 nanometer from the wall, that is relevant for mesoporous materials, the molecule wall interactions are of negligible importance and molecule interactions come into play. Therefore, for all the examples we consider for microporous metal organic frameworks, molecule wall collisions are dominant. The insights into the diffusion of gas molecules in metal organic frameworks is obtained on the basis of MD simulations. The simulations have been performed with a wide variety of gas molecules in several different metal organic frameworks. The data are available in the publications listed here. The MOF frameworks are not rigid and have some degree of flexibility, as illustrated in this animation for IRMOF 1. Some MOFs, such as MIL53, undergo structural changes in the presence of gas molecules, in this case carbon dioxide. MIL53 structure collapses in the presence of water. Let's look at the motion of benzene in 3 different microporous materials. Within the 8.5 angstrom lozenge-shaped channels of MIL47, you see benzene molecule has a rotational freedom and also experiences a somersault. This type of somersault is verified by neutron scattering experiments. The benzene somersault also occurs within the 7.3 angstrom channels of AFI zeolite. The channel shape is shown here. It's a 12-ring zeolite with the dimensions 7.3 and 7.26 in this direction. Within the intersecting channels of MFI, the benzene molecules are located at the intersections between the straight channels and the zigzag channels. And they also rotate freely. The preferential location of benzene at the channel intersections have severe consequences for the diffusivities of partner molecules, and this phenomena is explained in the video for MFI zeolite that is available on this channel. Magnesium MOF 74 has one-dimensional channels that are hexagonal in shape and have a size of 11 angstrom. The unsaturated magnesium atoms are exposed and can bind with guest molecules such as CO2, with alkenes and alkynes. Magnesium MOF 74 has potential applications for carbon capture and for alkene-alkane separations and alkyne-alkene separations. Let's have a look at the motion of hydrogen molecules within the channels. Hydrogen is poorly absorbed and gets reflected on striking the channel walls. Carbon dioxide absorbs strongly with one of the oxygen atoms binding with the metal atoms, and the motion of CO2 is shown here, where you will note that there's a higher concentration or near the walls, and once a CO2 molecule detaches from the exposed metal atoms, it experiences a trajectory that is akin to that of a boomerang before it returns to the metal site. The boomerang trajectory of CO2 has been experimentally verified by means of NMR data. The binding energies of guest molecules with the unsaturated metal atoms of magnesium MOF 74 are quantified by the isosteric heat of adsorption, and the hierarchy of binding energies is as follows: hydrogen, followed nitrogen, methane, ethane, propane, butane, carbon dioxide. And if we examine the MD data for the diffusivities of these guest molecules, they appear to correlate very nicely with the isosteric heat of adsorption. Therefore, the stronger the binding, the lower is the diffusivity. Put very simply, sticky guests have lower mobilities. Let's have a look at the motion of methane, carbon dioxide, and normal hexane with an IRMOF 1 that has large cages separated by large windows. Note that CO2 hovers around the vertices of these cages. The vertices are the locations of the unsaturated metal atoms. Here's a plot of the self-diffusivities of various gas molecules as a function of the component loadings. The hierarchy of diffusivity values is the inverse of the hierarchy of the isosteric heats of adsorption that reflect the binding energies. In other words, stronger the binding, lower the diffusivity. For example, CO2 has a lower diffusivity than methane because of its stronger binding with the unsaturated metal atoms due to Coulombic interactions. We turn now to the motion of gas molecules in copper BTC. The structure is rather interesting and fascinating. It consists of large cages separated from adjacent large cages by 9 angstrom windows. The large cages are also connected to tetrahedral pockets through openings that are about 4.6 angstrom in size, and the openings are triangular in shape. There are 8 tetrahedral pockets per unit cell. Let's have a look at the animations for methane motion within the cage window structure of copper BTC. The methane molecules are able to enter the tetrahedral pockets through these triangular 4.6 angstrom windows. MD simulation data for the self-diffusivity of methane in copper BTC as a function of loading is shown by the red circles. Interestingly, at a loading of 32 molecules per unit cell, the self-diffusivity of methane exhibits a maximum in the Now, the tetrahedral pockets are preferred locations for methane, and since there are 8 pockets per unit cell and the maximum loading per pocket is 4 methane molecules at a total loading of 32, all the preferred locations within the tetrahedral pockets are fully occupied. An increase in the loading of methane will force methane molecules to occupy the large open cages. In large open cage structures, the diffusivity invariably decreases with increased loading. Further explanation of the reasons behind the maximum and decrease is provided in this article. The isosteric heats of adsorption are plotted by the green squares here, and up to a loading of 32 molecules per unit cell, we see that the isosteric heats of adsorption are higher due to stronger interactions with the walls of the pockets, and then the isosteric heats of adsorption tends to plateau out because the interactions of methane with the large cages is less strong. Animations showing the motion of ethane, propane, normal butane and normal pentane show that all these linear alkanes can enter the tetrahedral pockets by entering it in a lengthwise manner. The tetrahedral pockets are also preferred locations for these linear alkanes, but the maximum loading per pocket decreases with increasing chain length. And the data on the self-diffusivities of C2, C3, NC4, and NC5 also show a maximum at a certain loading, and that loading at which a maximum occurs is different for each molecule because the maximum capacity within the tetrahedral pockets decreases from C2 to NC5. Let us have a look at the motion of isobutane, neopentane, and 2-methylbutane within copper BTC. Due to their configurations, the branched alkanes have greater difficulty in entering the tetrahedral pockets because of the constraint offered by the 4.6 angstrom window. The diffusivities of these branched alkanes are significantly lower, therefore, than the diffusivities of the linear alkanes shown in the previous slide. Let us summarize the story that has emerged so far. Sticky molecules with strong binding strengths have low mobility in the structures we have examined. Molecules that are poorly adsorbed have higher mobility. And the question is, what happens in a mixture of guests consisting of sticky molecules such as carbon dioxide with non-sticky molecules such as, say, hydrogen or methane? We now consider mixture separations in fungicide zeolite. This is the all-silica version consisting of an 11 angstrom cage separated by windows that are about 7.3 angstrom in size. More commonly used are the cation exchanged versions, sodium Y and sodium X. NaY contains 54 extra framework cations sodium per unit cell and has a silicon to aluminum ratio of 2.55. NaX has 86 sodium cations per unit cell with a silicon to aluminum ratio of 1.23. NaX is more commonly known by its trade name 13X zeolite. This graph shows the CO2 methane adsorption selectivity as a function of occupancy for all silica fungicide, sodium Y, and sodium X. With increased amounts of extra framework cations, the adsorption selectivity is increasingly in favor of CO2 because of Coulombic interactions. However, with increasing extra framework cations, the diffusion selectivity for CO2 with respect to methane is reduced from say about below unity by about 1 order of magnitude because of the reduced mobility of the strongly bound CO2 within the frameworks of cation exchange zeolites. There is also another effect of the increased binding of CO2 on the motion of its partner molecules, and that we shall consider in the subsequent slide. This animation shows the motion of gas molecules CO2 and hydrogen, shown by the white spheres, along the 1D channels of magnesium MOF 74. The more strongly adsorbed CO2 prevents hydrogen from traversing long distances along the 1D channel. The slowing down of hydrogen due to the presence of more strongly adsorbed CO2 is shown here in the MD data for the self-diffusivities in a mixture of CO2 and hydrogen at a constant total loading. And we note that with increased concentration of CO2 in the adsorbed phase, the hydrogen, the self-diffusivity decreases by a factor of 2. This slowing down effect is very commonly observed in mixtures of strongly adsorbing components and weakly adsorbing components within structures that are not strongly confined. This is a picture of traffic moving in the busy streets of Pune in India. The slow-moving elephant lowers the mobility of this scooter. For a mixture of carbon dioxide and methane diffusing within the 8.5 angstrom 1D channels of MEL 47, the most strongly adsorbed CO2 reduces the mobility of the more mobile partner, because CO2 does not vacate the adsorption sites quick enough for methane molecules to pass through the channels. Within the 12-ring channel of AFI zeolite, the most strongly adsorbed CO2 slows down the mobility of partner methane molecules. So the animation showing the motion of CO2 and hydrogen, the intrinsically more mobile hydrogen is prevented from bypassing the carbon dioxide molecule that is strongly adsorbed, and therefore effectively its mobility within the channel is reduced. The M atoms of MOF 74, where M is either magnesium, iron, cobalt, nickel, or manganese, selectively bind with alkynes such as ethyne and alkenes such as ethene and propene. This selective binding allows selective adsorption of alkenes from mixtures with alkanes and selective adsorption of alkynes in mixtures with alkenes. Consider separations of propene and propane mixtures in iron MOF 74. The animations of motion of molecules in the one-dimensional channels, yellow is propene and green is propane, are shown here. Propene is more strongly adsorbed and has a slightly lower mobility than propane. In the mixture, propene has the effect of slowing down propane. The octane number of isomers of hexane increased with the degree of branching, and the di-branched isomers 2,2-dimethylbutane and 2,3-dimethylbutane are preferred components for incorporation into the gasoline pool for making high-octane gasoline. In industrial practice, a mixture of C6 isomers is fed to an isomerization reactor wherein the linear alkanes are converted to the branched alkanes. Now, we need to separate the desired di-branched hexanes from the linear hexane and the monobranched hexane in an adsorber. We recycle the linear and monobranched hexanes, 2-methylpentane and 3-methylpentane, back to the isomerization reactor. And the focus now is on the separation of hexane isomers to into two fractions, one in which we have the di-branched isomers and the other in which the linear and monobranched isomers are fed back into the isomerization reactor. A candidate metal organic framework that is able to meet the separation tasks required by industry is Fe2BDP3 that has triangular channels of 4.9 angstrom in size. The isosteric heats of adsorption of the hexane isomers in the 4.9 angstrom triangular channels of Fe2BDP3 are shown in this graph here. The hierarchy of binding strengths is normal hexane, 2-methylpentane, 3-methylpentane, and the di-branched isomers 2,2-dimethylbutane and 2,3-dimethylbutane. The linear hexane molecule can align itself along the vertices of the triangular channels, which each of the carbon atoms effectively interacting with the channel walls. The van der Waals interaction of the more compact monobranched and dibranched isomers are lower in strength than that of the linear isomer. Breakthrough experiments show that the hierarchy of breakthroughs follows the hierarchy of binding strengths. The di-branched isomers are the first components to break through, followed by 3-methylpentane and 2-methylpentane, and finally the linear hexane molecule breaks through the fixed bed adsorber. Therefore, Fe2BDP3 can be used as adsorbent in a PSA scheme shown in the previous slide, wherein the first two components that are rejected into the gas phase can be removed and incorporated into the gasoline pool, and the adsorbed components can be desorbed and recycled back to the isomerization reactor. Let's consider the traffic of linear hexane and monobranched isomers 2-methylpentane and 3-methylpentane as it moves within the triangular channels of Fe2BDP3. The mobility of the linear hexane molecule is higher than the mobility of the monobranched isomers, because the monobranched isomers are more strongly confined within the 4.9 angstrom channels, whereas the linear isomer is less strongly confined. A special feature of hexane separation with this MOF is that adsorption and diffusion proceed hand in hand, because hexane, which has the highest adsorption strength, also has the highest diffusivity value, and this combination of adsorption and diffusion being synergistic is useful in fixed bed separations. The di-branched isomers 2,2-dimethylbutane and 2,3-dimethylbutane have compact configurations and are very strongly confined within the triangular channels. Their diffusivities are even lower than those of the monobranched isomers. The combination of poor adsorption strengths and low diffusivity values makes for earlier breakthroughs in fixed bed adsorbers, and this is desirable from a process standpoint, making Fe2BDP3 a viable candidate for commercial use. Molecular simulations have established that cobalt BDP that has 10 angstrom size square channels is capable of separating the isomers of pentane and the isomers of hexane, relying on differences in the van der Waals interactions between the alkane isomers and the pore walls. Let us try to obtain a feel for the motion of pentane isomers, normal pentane, 2-methylpentane, and neopentane within the channels of cobalt BDP. The channel dimensions of 10 angstrom are larger than those for Fe2BDP3, and therefore the differences in the diffusivities between the pentane isomers is minimal. These animations show the motion of normal hexane, 2-methylpentane, and 3-methylpentane within the square channels of cobalt BDP. The diffusivities of these isomers are nearly the same, and the separations are largely based on differences in the van der Waals interactions of the alkane isomers with the pore wall. Here we look at the animations for the motion of 2,2-dimethylbutane and 2,3-dimethylbutane in cobalt BDP. The diffusivities of these di-branched isomers are nearly the same as for the linear and monobranched isomers, and the separations of hexane isomers is purely on the basis of van der Waals interaction. Indeed, this is confirmed by molecular simulations for a 5-component mixture of hexane isomers, we see that the component loadings in cobalt BDP follow the hierarchy normal hexane, 2-methylpentane, 3-methylpentane, 2,3-dimethylbutane, and 2,2-dimethylbutane. This allows the use of cobalt BDP as an adsorbent in the PSA scheme for octane upgrading.